Okay, so yeah, Arvid Axelsson, student. So Master of Forestry, if you didn't know that already. This is sort of a preview of the results from my master thesis. It's not done yet, so it's not a final presentation. This is a presentation that I made for Map Days in Örebro. That was 2 weeks ago? 1 week ago? 2 weeks ago? Oh, okay. So it was the 28th of March, and I have updated this a bit with new results because I'm not done yet, so I've updated it. It's also not very. I didn't make this presentation for foresters, but for people that have no idea what forestry is. So I gave sort of a background on some ideas on remote sensing in forestry. But I'll just do it the same way, almost the same way that I did it in Örebro. So today we have very good maps of the forest, but this is mainly volume, height, and basal area that we can measure. And it's primarily made with LiDAR, these kind of maps made by Skogsstyrelsen. And to do this, we take a plane and we fly, and we get a point cloud in 3D. We relate that point cloud to these metrics that we want from the forest. The big bonus in this is that we can automate the process. We don't have to go to each site and measure. We can do it once, and we have covering data for all of the scanned area. What's missing from this is information on the species. And around half of the red-listed species in Sweden are tied to deciduous trees. For example, ekoxe, don't know the English name. Yeah, so there are beetles that are tied to oaks, and aspordveckor, so other type of insect is tied to aspen. So the point is that tree species is very important for what kind of habitat there might be at one place. If there is one type of tree species, we can expect some types of insects and other things, but if it's another tree species, we can expect to find other insects too. The Skogsstyrelsen. The Forest Agency of Sweden have inventoried key habitats, and that's woodland areas where you can expect to find endangered and red-listed species that have very high conservation values. And a rough estimate that they themselves have made is that around half of the key habitats has been inventoried as such. Rest of them are distributed across the landscape, and they don't really know where they are. And since we can tie tree species to habitats, it is very interesting to find where there are certain tree species, so that we can find these types of habitats that are important for conservation purposes then. So this is the common remote sensing picture when you have tree species. We have pine, we have spruce, and we have other. And this isn't...
You got it so good.
This isn't really very good if we want to find something that's tied to oak, because we don't know if it's birch or oak, and that's a problem. And anledning. The
Reason.
reason why it's this way is because these kind of species often look kind of the same in an aerial photography or a satellite image. They look very alike. So what I have been doing is I have looked at multispectral ALS. And that's an ordinary laser scanner, but it has 3 wavelengths that it uses. It's 1064, 1550 and 532 nanometers. And they are scanned in sort of different angles, so they might differ a bit, but it's 0, 3.5 and 7 degrees forward, tilted forwards on the plane. And it's around 20 points per square meter per channel, so it's a very, very dense point cloud with 60 points per square meter in total. And this is a new technology that was first used in 2015. So there haven't been very much studies made on the data set. This is the first scanning that has been made in Sweden. This and curriculum. It's part of the same project. And here are how the different trees can look in the point cloud. We have alder, ash, birch, oak, spruce, cherry, linden, maple and pine. And they sort of look quite different. Spruce is very easy to spot, and pine, but the rest are, they look quite alike, but not really. So this is just the structure, the trees, and we also have intensity metrics in 3 colors. So here I've colored them red, green and blue, and the intensity of each point is the intensity of the return. And we can see that there are more high intensity points at the top of the crown and less at the bottom of the crown. And this might differ between tree species too. The idea is that ash, for example, is quite sparse in the crown, while maple, this is maple, have a quite thick crown, which is harder to penetrate. So the data that I used in the field, I collected in these kinds of areas. These are the cows of Rämningstorp. And we see here the trees in the background are quite large and solitary. So I went around them with a GPS to delineate them, and then I used those coordinates to clip them from the point clouds. It's not really representative of trees from the forest because they don't grow like this, but it's just a pilot study to look at if we can see differences in tree species with this kind of data. I used 179 trees that I measured, and I also measured crown height, height to the first living branch, and just height and tree species. So I then had to analyze the point clouds in different ways. I did this in 3 ways. First was I constructed ellipsoids in the trees. So I fitted an ellipsoid to the crown, so I cut away everything below the crown, and then I fitted this oval shape and sliced it from the outside and in. So I got layers like on an onion, and I counted the density of points in each layer and the intensity in each layer, and got that as metrics for each tree so that I could make a linear discriminant analysis on those. Then I also made the same thing but with constant layers. I calculated density for each layer and intensity for each layer. And then I also looked at the classical percentiles that are commonly used in remote sensing LiDAR. So I looked at percentiles of height and intensity. And these are the results. I made some subsets of the data. The first row here is all the points together in each point cloud, and we see that the best classification is made with the percentile method. This is partly translated ellipsoid, layer, and percentiles. Yeah, and then I subsetted the intensity values from that. So only intensity values. We see that we get sort of a good estimation anyway. It's the same for percentiles because these are only intensity values. These are not any structure values. Yeah, and here in structure and merge cloud. Structure, I subsetted the structure metrics for different channels. In merge cloud, I put all the clouds together into 160 point per square meter density cloud and made only structural metrics on that cloud. So here in the percentile method and the layer method, we can see that there is better to split them if we want to classify tree species a bit better. And that might be an effect of different footprints from the laser and different reflectance that makes points visible or not, different intensities. And this is good to find for people that want to buy wood for special purposes. For example, maple is used for violins. That's a special kind of wood that you could find if you have information on tree species. We can find, as I talked about from the beginning, different key habitats. These are key habitats around Stockholm. And we can also get a better landscape, a better view on the landscape as a whole for nature conservation. You can see that we have 5 oaks here and 50 here. Then we can remove these and just keep these, for example. So that's it. That's the whole presentation, and I also had some